All right, so before we go into the strong duality theorem, I just want to point out that the proof for the weak duality theorem does not use any special properties of tree networks. Everything here is really not special to a tree network, but it works also for general networks. And for this reason, the weak duality theorem actually applies to general networks as well. Okay? Please make a note of that. However, the strong duality theorem will use actually the tree network properties. Okay, the strong duality theorem is only applicable to tree networks, and you'll see why when we go through the proof. But first, let me give you the statement. Let's just also add this statement here. What we're going to discuss right now will also justify the correctness of the algorithm dual opt. Given ZP, the optimal objective value for the P-center problem, where P is restricted to integers between 1 and less or equal n minus 1. The set K star constructed by dual opt satisfies the following equalities. K star is an optimal solution to the dual problem, so it achieves the optimal objective value. So it does maximize g of k over all those k in Cp plus 1. That was the definition of the dual problem, okay? Which is also equal to, so g of k star is also equal to Zp, which is equal to the minimum objective value of the P-center problem. So before I start proving the strong duality theorem, I want to note a corollary to the weak duality theorem. So this is a corollary to the weak duality theorem that we stated here. If X bar is a feasible solution to the P-center problem and K bar is a feasible solution to the dual of the P-center problem, and if it also happens that f of x bar is equal to g of k bar, then what is the conclusion? Then they are optimal, right. Then x bar and k bar are optimal to their respective problems, to the P-center and dual of the P-center problem. This is an immediate consequence of the weak duality theorem, because in the weak duality theorem, you always have g of k less than or equal to f of x. You're trying to maximize g of k, you're trying to minimize f of x. So whenever you have on hand a solution x bar and a solution k bar, that are both feasible and equal in objective values, then of course that's the best you can do, because one is always a bound for the other. When they meet, that's it. You cannot do any better. Okay. So let's go through this proof of the strong duality theorem now. Okay, in the statement of the strong duality theorem, I have only information about ZP and some K-star solution found by the algorithm dual-opt. And the claim is, well, then ZP bar is equal to G of K star, which is the maximizing value for the dual problem, which is also equal to the minimum objective for the primal problem. And this is just the definition of the ZP, that's all, okay? So let's begin with a solution X star to the P-center problem. So let X star be a feasible solution to the P-center problem, and in fact, let it be an optimal solution. We know that there's always an optimal solution to the P-center problem, so we just pick one, okay? Then, of course, by assumption, X star has P points in it, and the loss f of X star is, in fact, the minimizing value ZP. I know that ZP is always greater or equal alpha, so there are two cases arising from that. One is the equality case, the other one is the strict inequality case. So let's go through the first case. ZP equals alpha. In this case, my K star is chosen in step 1 of the algorithm Duality. Remember, whenever ZP is equal to alpha, you pick your K star in such a way that you take the index S, which supplies the value of alpha in K star. Okay? So K star is chosen in step 1 of Duality, which implies or so that the cardinality of K star is indeed P plus 1, because I just picked some P plus 1 vertices in the tree, and alpha is equal to Fs0 for some S, and because I include S in K star, it's also equal to alpha of K star. Okay? Because S is in K star. So we have alpha, which is equal to alpha of K star by construction of K star, which is less than or equal to G of K star. This is simply from the definition of G of K. G of K star. G of K star is the maximum of alpha and beta of K star, so it's greater or equal to alpha of K star. By weak duality theorem, I have G of K star less than or equal to f of x star. And by assumption, x star is an optimal solution, so f of x star is equal to ZP. And we assumed, in case 1, ZP is equal to alpha, so everything is equality here. Done for this part. So let's go with part 2 now. Okay, let me begin here. In case 2, ZP is greater than alpha. This case is a little bit involved, so I want you to be patient, okay? Because there are quite a bit of arguments to go through. Okay. First, I'm going to define a set R cap, which has in it all those beta ij values that are in R. What is R? Does everybody remember? R is the set of all beta ij's, all possible beta ij's. Okay? So we pick R cap to be the subset of R which has those beta ij's that are greater or equal ZP. Okay? So the algorithm Duality solved the covering problem by picking a value z. And what was special about z? Z is chosen to satisfy the inequalities zp prime less than z, which is less than zp. That's the second step of the algorithm. Let me actually take it up. And what was ZP prime? ZP prime was the largest value in R, which is less than ZP. Okay? So, since Z is chosen to satisfy these inequalities, we have the following conclusion. Then there's no beta ij in the open interval defined by ZP prime and ZP, which means that whenever beta ij is greater or equal ZP, that's the case in the definition of R cap. This also implies that this sort of beta ij is greater or equal, actually, ZP. Sorry, I want to change that, just a second. Whenever beta ij is greater than Z, this implies that beta ij is greater or equal ZP. Does everybody agree with that? This is how you should think about this. Here you've got a value ZP, then you've got the next smaller value ZP prime. So you've got other numbers possibly in the set R, but there's nothing in the open interval here. No beta ij in that particular open interval, which means that whenever beta ij is greater than the Z value you pick here, of course, that beta ij will be somewhere on the right side of ZP, okay, greater or equal. Okay, that's all we are saying. So I can revise or I can also claim that R cap is the set of beta ij values in R for which beta ij is strictly greater than Z. That's the definition. This is something that you deduce. So let U be the distinguished set of vertex indices or vertices found by the algorithm cover. In solving the problem C of Z. What am I talking about? What am I talking about?
Use the dual to the cover.
Right. Well, no, this only has to do with the algorithm. In the algorithm cover, we pull these strings tight, and as soon as the endpoint of a string reaches some point along the edge under consideration, you locate a point there. And that sort of a string was put into a special set, which we called U. Okay? So U is the set of distinguished indices. These are critical indices that we identified, and that's why I refer to them as the distinguished set. Okay? So I know that the distinguished indices, or those indices in the set U, satisfy the following inequality. Distance between Vi and Vj is related to Ei of z and Ej of z in some way for every distinguished pair of indices I less than j. What's the relation? Strictly greater than that. Why is that true?
Because otherwise those two indices will be covered by a single center. So they will be in U.
Okay, true. This is true for the following reason. Here you've got a certain edge under consideration. This is the tip of the green tree under consideration. So rest of the green tree might be somewhere here. I don't know. I've got possibly some brown tree here. That's the vertex you've chosen at some iteration, for example. Then you pulled some strings tight here, and it reached, say, here. So you located, say, some xj here. Okay? As soon as you located that string, it was coming from some vertex vj here. Okay? V bracket j. So you put j in u. As soon as you do that, you add that bracket j to the set being constructed. Okay? So, or to the distinguished set.
Are they two vertices?
Pardon?
Are they two vertices two side of xj in the class?
It doesn't matter. This is the green tree. This is an edge of the green tree where that's a tip vertex, a leaf vertex of the green tree. This one is the adjacent vertex. So you try to pull these strings tight towards the adjacent vertex. Okay? That was the mechanics of the algorithm. There may be a green tree here or not, but nevertheless, this is how we were working this out. Is that what you're asking, or are you asking something else?
You answered my question.
Okay. What did you ask then?
Are they vertices? I asked the points.
These are vertices, yeah. Yeah, they are vertices. All right, so I browned this portion, and I put that index into my distinguished set that was constructed up to that point in time. And as soon as I located xj, I checked all those strings that are resident in the green tree to see if they actually reach xj. If they reached, I assigned them. In other words, I assigned those vertices as being coverable by xj because those strings do reach. And as soon as you identify such strings that do reach, you drop them from further consideration. So that as you move along, when I is less than j, this should be the situation because at the time I was included in the distinguished set. J was a vertex whose string was checked. It was surviving up to that point, and it did not reach because later on it actually caused a later subsequent new point to be located. Okay? For that reason, it's obvious that it did not reach. If it did reach, this would be less than or equal to, because it does not reach, of course, it's this way. That's the critical thing that you should see in your head. Okay. So let's call that statement 1. 1 implies that beta ij for that particular ij pair is greater than z. In fact, this is true for every ij in U where I is less than j. Now, the important statement here is beta ij being greater than z for distinguished vertex indices. You may or may not see it immediately. I'm going to explain why, but that's the claim. First, let's make the claim. When you write something strong, first state what you're trying to prove or what your claim is. If you don't do that, if you try to lead into the final conclusion, it gets boring. And without knowing where you are leading to, nobody will be able to. Sometimes, people have difficult time following through your arguments. But if you tell what the claim is at the beginning, or somewhere along the lines, then it will be easier. So, anyway, from 1, I can make this deduction. Does anybody have an immediate answer for why this is true?
I think for the same reason. If Bij would be less than or equal to z, then ij in U would have been covered.
Okay.
Same center.
I see. In computing beta ij, actually, I'm just considering a particular pair, I and j. And yeah, but okay, that's a good answer. Nevertheless, it doesn't give the entire story, so let me go through this. But that's the basic idea. However, that's a pictorial justification for the thing rather than a rigorous one. So let's just justify this. This follows from the fact that beta ij, when I and j come from U, it's the z1 value for I and j. It's the optimal one-center solution value, objective value for vertices I and j, which is by definition the minimum of, say, lambda subject to distance x vk less than or equal to uk for k equals I or j, and fk of dx vk is less than or equal to z for, again, k equals I in j. This is the definition of beta ij. Which is equivalent to, so I'm writing equality here, that entire optimization value is equal to the minimum value of lambda subject to dx vk being less than or equal to ek of z, k equals I or j. We're using the same thing. The distance constraint together with the loss value bounded above by z, these inequalities, pairs of inequalities, are equivalent to the distance being bounded above by the new function ek of z. We've done this before, and we're still doing the same thing. Okay? Where the definition of ek was given to you before, with x and t, of course. So that with lambda set equal to the minimum feasible value beta ij, the inequalities dx vk less than or equal to ek of beta ij. I have two inequalities here, k being equal to I or k equal to j. And each time the right side is defined by ek of beta ij. So the first inequality is dx vi less than or equal to ei of beta ij. The second inequality, ej dx vj is less than or equal to ej of beta ij. No, let me just continue, then you can ask, okay? The inequalities stated here hold for some x in t. In other words, there's a feasible solution to this. Now you can ask your question.
What is lambda?
Lambda is just a variable that's being minimized. Oh, sorry. Okay. That's lambda. Sorry about that. Yeah, that's lambda. I'm just minimizing lambda, where the right sides are defined as a function of lambda. Okay? That was a good question. I should have allowed you to say it first. Okay. All right, so because beta ij is the smallest lambda for which the constraints hold, then of course when you put lambda equals beta ij, these constraints do hold. So there's a solution x that satisfies these constraints. Okay? Hence, we have the following. I've got ei of z plus ej of z. This z is the particular z we picked in solving the covering problem. Okay? ei of z plus ej of z is less than distance between vi and vj. Why is this true? This is true because of 1. In 1, we actually argued for that. Whenever I and j are distinguished indices, we've got that. Okay, so that comes from 1. Now we know that this distance is less than or equal to distance vi to x plus distance x to vj. This is due to triangle inequality. Triangle inequality, and I know that each of these distances are less than or equal to the upper bounds defined by ei's, ei of beta ij plus ej of beta ij. This comes from here. So what I proved, well, I did not prove anything yet. What I did is I have a series of inequalities here. And this simply says that ei of z plus ej of z is strictly less than ei of beta aj plus ej of beta ij. Now, what kind of a function is ei and ej? Up to a certain point, and then after that it's flat. It's non-decreasing. So because you have a non-decreasing function, this is non-decreasing, this is non-decreasing. So what can you conclude here? Which implies that z is less than beta ij. In case you don't feel comfortable with that, all you have to do is you can view this as a new function. You can call it, for example, EI plus EJ. You can name it that way, okay? Evaluated at the same argument. So EI plus EJ of z is defined by EI of z plus EJ of z. That's how you define. And when the component functions are non-decreasing, then of course the sum function is also non-decreasing. Okay? Similarly, you've got the same thing here. So EI plus EJ is evaluated this time at some other number, beta ij, and this evaluation is strictly smaller than that evaluation. And when these functions are, when the function is non-decreasing, of course, then it should be this way. Okay? So I just concluded beta ij is indeed greater than z for every distinguished pair of indices coming from U. Let's call that expression 2. We have then r cap, well, we have each such beta ij in r cap. Because we said whenever beta ij is greater than z, it should be in r cap. That was one of the statements we've done at the beginning. Okay? So let the cardinality of the set U found by cover be Q. Clearly, this cardinality is greater or equal to P plus 1. Why? Because the Z value you picked is between Z prime P and ZP. So Z is less than ZP implies you have to have at least one more point, which means you have to have at least one more vertex that supplies the point. Okay. So in constructing U, the Duality algorithm chose the constructed set K star as any subset of U, that's step 2 of the algorithm, as any subset of U consisting of some p plus 1 elements of U. Accordingly, K star by construction has p plus 1 points in it, or vertex indices in it. Which means that K star is feasible to the dual problem. So first we established feasibility. Then we also have the following. Zp is, by assumption, equal to f of x star. Why by assumption? Because I assumed x star is an optimal p-center solution at the beginning. Okay? So this is by assumption. I know that this is greater or equal g of k star because of the weak duality theorem. I have a feasible solution to the p-center problem. I have a feasible k star solution to the dual solution, dual problem. So weak duality says you've got this inequality. This is greater or equal beta of k star. Because g of k star is the maximum of beta k star or alpha k star, so this is from the definition of g of k star. These are all elementary facts. We're still continuing though. This is greater or equal beta of u. Why? Because u is a larger set than k star. It contains all elements of k star, so the minimum beta you would get here would be smaller or equal that. Okay? So this is from the fact that k star is a subset of u. They could be equal, of course. Okay? And finally, this last expression, beta of u, is greater or equal minimum of beta ij when beta ij is restricted to r cap. Why is that true? Because of 3. Because beta ij is in r cap whenever ij are in u and I less than j. So when you take the minimum over all possible beta values in r cap, well, r cap certainly includes the beta ij's coming from u, but it may include other ones. So for that reason, this minimum is certainly, in the worst case, less or equal that minimum. Maybe I should change these beta ij's to, let's make them KL, you know. We're just talking about generic index pairs here. Okay? All right, so we've got this from number 3. And finally, this one is greater or equal ZP. Why is this true? Say it again.
That's the optimum.
That's the optimum, but why is the inequality true? Because that's how I defined R cap, actually. That's from the definition of R cap. Because when I defined R cap, I defined it to be those beta ij values whose beta ij's values are greater or equal ZP. So the minimum here is certainly greater or equal ZP, just from the definition. So what did I do? I again have a series of inequalities with lower and upper bounds being the same, so everything is equality. So all inequalities hold as equalities. And one of those equalities is f of x star equals g of k star. The corollary to the weak duality theorem implies you have a feasible solution x star to primal, a feasible solution k star to the dual, and they have equal objective value, so they must be optimal. So the corollary to the weak duality theorem implies k star is optimal to the dual problem. X star is already optimal by assumption because that's how we picked it. Note also that actually the proof is essentially done here, so I can just finish it up here, but there's one more thing you can notice here. Zp is indeed equal to the minimum beta ij or beta kl value, where beta kl comes from r cap. That's one of the, well, these are equalities, so that's another equality here. Okay? Zp is equal to that. What's the importance of that? It simply says that Zp is indeed coming from the set R. That's the finite dominating, we had that claim without proof. So I told you that actually the optimal objective value comes from a finite set of values. We never proved it, but that one actually does the job. So we finish it up here. Wow, we are out of time. Yes, question.
I don't understand why P beta of U is greater than or equal to
Because whenever ij comes from U, the corresponding beta value is in R cap. We've arrived at this conclusion before, which means that the beta ij that supplies beta of U is certainly in R cap, okay? But then R cap may include other index pairs that are not necessarily in U, so it's a larger set. And so the minimum over a larger set will induce that inequality. Does that make sense? Okay. References for nonlinear P-center problem and duality, related duality. One is the paper I cited before by Tansel, Francis, Lau, and Chen. This is the OR paper, Operations Research paper, published back in 1982. I think I wrote down 83 before, so please correct that. It's 82. Volume 30, pages 725 to 743. And the other reference is also by Tansel, Francis, Lau. This time there is no Chen. This one is the chapter 8 of the book Discrete Location. This is a book edited by Merchandani and Francis. Publication date is 1990, and it's a publication, a book by Wiley and Sons. Okay? I think this book chapter is more instructive. It's because when you write things for books, you know, you spend more time explaining stuff. In papers, you don't have that much time. Okay. And next time, maybe we'll discuss a little bit more about the algorithmic complexity of all of these issues, and then we'll probably continue with p-medium problems. Okay.